We're having our last lecture today, and this will be a brief comment, only a brief comment on the existence of the so-called topological phase transition, which occurs in a two-dimensional XY model, the model of planar spins, without any symmetry, spontaneous symmetry break. There is no local order parameter in this case, because the average magnetization in two dimensions with any continuous group, whether SO3 symmetric or A2 symmetric, doesn't matter. What matters is the group is continuous, the symmetry is continuous. The other parameter, local order parameter, vanishes as before due to fluctuations. Nevertheless, in this disordered phase, from the point of view of magnetization, there is a phase transition which splits the phase diagram in two parts. One, both are disordered, both phases are disordered. The low temperature phase is characterized by algebraically decaying correlations of the spins. Therefore, it is critical. And not only at the point, but in the whole range. But at high temperatures, we expect a finite correlation length to appear. And this is there is a problem for you here in the text of my lectures to show that at temperatures well above the exchange coupling J, a simple calculation shows that the correlation function N of delta and 0 basically follows this law. It's an absolute value of R divided by some psi, which is a function of T, I believe, such that psi of T is finite, and therefore we obviously have a characteristic length scale which is absent if the temperature is well below J. In other words, there should exist a special point on the temperature scale where a kind of phase transition occurs, at which the finite correlation length appears, at which the originally infinite correlation length transforms to something finite. And that transition is a topological nature, therefore we have to carefully understand what has been missed in the Gaussian approximation. But before we turn to that, let us comment on what is written here. If I look at this average has actually cosine theta r minus theta 0. Since I am at high temperatures now, of course the thetas are angular variables. By no means this can be treated as Gaussian fields. These are just angular variables varying from 0 to 2 pi on a circle, and no continuous limit can be taken. And the action, which is the Hamiltonian in units of temperature, has the form. It's right. Let me write it like this: K divided by 2, sum over the nearest neighbors, and the cosine theta r minus theta r prime. Well, in fact, what we are after here is the real part of this spot, which is nothing but the real part of something which looks like this. It's a product of all latest size, the integral from 0 to 2 pi. Let me write down something like I from 1 to n is the total number of latest size, the theta I divided by 2 pi. This is my integration measure. This is the way I define, if you wish, the functional integral. I integrate over all the speeds, over all the angles from 0 to 2 pi at each lattice side. Then I have the function I'm interested in, which I want to average. Right? And here I have the action, minus k divided by 2. I write it down again. Cosine theta r minus theta prime. And divided by the same what is written here, but only with this term. Now this is quite a general definition, actually. I could have proceeded in this way without any reference to the temperature, whether it's large, high, or down, or low, because it's an exact expression. We know that this expression significantly simplifies at low temperatures when we can pass a continuum description, but it's a completely different story. This is an exact expression, exact. Right? Now, when temperature is high, that means that the parameter k, which is j divided by t, is very small. And therefore, what is written here, this action can be replaced, the exponent of action, of minus action, can be replaced by 1 minus action itself, as a matter of fact, plus higher order terms. The action is of the order of k. K is a small parameter, therefore it is 1 minus k divided by 2. Some, I can write down jk if you wish, cosine theta j minus theta k. And jk plus ok squared. J and k are nearest neighbors. So in fact I can expand at high temperatures when k is small. I can replace this by this. This is for sure. Now, the first term gets out. A very simple observation, because if I replace this exponent by unity, then the average of this exponent is 0. Because the cosine or the sine or the angle averaged over the interval is 0. Right? Moreover, if I have an integral from 0 to pi, d theta divided by 2 pi, what kind of terms I may have in this expansion, if you carefully look? There may be cases when I have something like I, k, and theta, when k is some number. 1, 2, 3, 1. When I expand everything and collect terms, I will have the exponents of this kind, including the term when k is 0. When k is 0, then what remains here, if this integral is I k, then I immediately conclude that I notice. I don't have this exponent, this is simply the length of this interval, the circumference of the circle divided by 2 pi squared. Now for any k, no 0, this integral vanishes, just due to periodicity of this function. It's a trivial observation, right? So therefore, I of k is just delta kz. It's a chroma. That gives us a clue. Suppose this is a lattice we're interested in. And somewhere here I choose the point r equal to 0. And somewhere here, I have the observation point R. So theta R lives here, theta 0 lives here, theta R lives there. I start with the first term. And in this term, I have exponent minus I theta 0 here in the integral. According to this observation, I should find a compensating exponent, e to the power I theta 0, which being multiplied by this, give me 1, and then I will have a finite result. In any other situation, I fail, I get a 0. So the only contribution when the exponent is given, I have to find the conjugate exponent to be multiplied. In this case, I will get 1 number, and the result will be now 0. Now, how comes about? So, therefore, I have to single out from this expansion, the term which lives, say, on this link. This is 0, and this is some, call it 1. The term living on this link contains the cosine theta 0 minus theta 1, which is proportional to the exponent I theta 0 minus theta 1, and the exponent minus I theta 0 minus theta 1. I have to integrate over omega this exponent, of course. Which one? With the minus sign, right? With the minus sign. Of course, this doesn't help me, but this does. I immediately collect the term, the exponent with a plus sign. It gives me the desired result. But then this extra exponent minus I theta 1 is left over. What to do with it? Now I'm here. And I have a similar problem with this. So therefore I have to find another neighboring link, suppose this one, which will kill this term, but also generate an exponent of this type, plus or minus I to the power I theta 2. And this process will continue. I will have to go along some path. I'm just showing you a typical path which I can follow. To the right, up, left, 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 up, right, up, right. Here I came here. And every time I built a link, I have a corresponding K in front because this is an expansion of this type. The whole path will be characterized by the number of links of which the path is comprised. And then I have to take K to the power of that number. Don't forget, K is small. The larger is that number, the smaller is the result. So the largest result, therefore, will be contributed by the path of the shortest length. Right? There may be more than one such paths, but not too much. For instance, if I have such a problem, this is the original point, this is the final point, you just calculate 1, 2, 3, 4. This is one path. 1, 2, 3, 4. Another path. 1, 2, 3, 4. You see, all of them are degenerate. All of them, if I go just along this very, very simple picture, they are degenerate. But if I increase the number of the distance, then you can see that, for instance, obviously this path is not the optimal one. I can find a short path. So, it is absolutely clear with this observation. You sit down, there is a problem, but this is an important hint for you. But this correlation function, the correlation function, gamma as a function of n, should be proportional to k when n is just that very distance, because if this is a distance, that any path, especially those paths which are the shortest path, will be of the order of this n. Right? It's a matter of proportionality. Well, with k being very small, you write down this is the same as minus n logarithm 1 over k. Now the logarithm is large. Right? And you do this following. You write down minus a n times a naught. And here you have a naught divided by the logarithm 1 over k. This is the construction you do. A trivial transformation. This gives me the distance. It's an exponent of the distance minus r. And this gives me the correlation length. So the correlation length is a naught and log 1 over k. So it's t divided by j. It's a large parameter. The logarithm is also large. Psi is less than a naught. You see a very, very short correlation. So in this way you get convinced that at high temperatures the correlation length has to be finite. Whereas we have already seen that within the Gaussian model at low temperatures the same correlation function displays not an exponential decay but a power law decay. And in mathematics there is no smooth way to pass from a power law to an exponential function. There should be phase transition, even in mathematics. So therefore we conclude that there should be a phase transition. Because we have two qualitatively different behaviors of the correlation function, despite the fact that this transition should not be associated with any spontaneous breakdown of the continuous symmetry. That's very important to keep in mind. This is topological transition. Now, so what have you missed in the Gaussian model? The Gaussian model, the one that we adopted, and which was defined by the action as not some constant, which I don't write, k divided by 2, integral d to x, and the gradient of the angular field, which is no longer an angular field, it's simply a scalar field, unrestricted, unlimited, unbounded field, as opposed to the original bounded compact field. This action was derived under assumption that the gradient of the field times the distance, the interatomic distance. What is that? This is a typical change nearest neighbors. This is a typical change of the angle at the distance comparable to the nearest neighbor distance. Right? If I take this gradient, I can multiply by the distance, it will be dimensionless quantity. If this is much less than 1, in other words, if at neighboring sides, the corresponding angle between the two vectors is small, this is precisely what this condition means, then I'm dealing only with smooth configurations, slowly changing at microscopic distances, and therefore this formula applies. There is a good question on what grounds I can discard higher order gradients. Think about it. You are now well educated to give an educated guess, not simply because it's an expansion. You may say, okay, you said delta theta effectively is small, therefore it will be a Taylor expansion. But how small? Think about more fundamental. This is a kind of critical theory with infinite correlation length. This. So therefore you can introduce the so-called primary field, strongly fluctuating field, defining scaling dimensions. You know which perturbations are relevant, which are irrelevant, so you have to think in these terms. If you show that higher order gradients can be discarded, using these arguments, that's fine. When one can buy this point of view, otherwise not. Right. So the configurations are smooth at short distances. The relative angles are small. But what about the angles between a given value of the vector field and somewhere far away from it? If you go a long way, then with these small relative, displacements, the misorientations, you eventually arrive at some completely different orientations of the vector fields, which may be of the order of 1, of pi divided by 2 pi, fraction of that, whatever. In other words, nothing precludes you to have a configuration which in some part of the plane, when the whole thing is being developed, this local magnetization vector undergoes a full rotation, say by an angle of 2 pi, along some path in plane. So again, this is what I have. I want to incorporate the possibility of having such things as what is called a vortex of this vector field. Of course, somewhere here, there should be a center of this vortex. And at short distances, what happens here, nobody knows, because if I go back to the latest description, as I said already, whereas at large distances from the center of this vortex, I can obey this condition. Close to the center, this breaks down. Because if I want to have all my vectors along the have a radial distribution, then I will have at the plaquette here, elementary square, something like this. You see the relative angle between the neighbors is now becoming of the order of pi divided by 90 degrees. By no means this is so like that. So configurations like this require certain regularization. They can be only incorporated into the scheme if close to the center, which is called the core of the vortex. You completely discard any theory like this and simply replaced by some what is called core, a hard core, which you don't know much about. It stays completely beyond this theory. Why I have already explained the day before yesterday. If you go to polar coordinates and want to classify, to specialize with these coordinates and describe all the points on the plane, you will succeed for all the points except for one, except for the origin. At the origin, the radius is 0, but the angle stays undefined. Very close, very similar to what we have. But now suppose I have such a configuration. I want to characterize what happens here. What actually happens here? In this picture, if I fix some original direction of my field, and I start moving along this closed contour, I think that my magnetization undergoes one full rotation. Right? So delta theta, in this case, is 2 pi. Right? To me, what is important, if I start with some local value of the magnetization and go along the path, whatever is going on in between, everywhere, when I look at the local distribution of those fields, everything should be smooth and non-singular. In other words, I might have a situation like this. If I start with this, you see what I'm doing now? Everywhere I'm keeping the continuity and the small gradient. Tell me what is the overall change delta theta in this case?
0.
It's 0. Can it be 0.25? Can it be 1.075? If you carefully look, what you may have, you can introduce this number q, which is delta theta, in units of 2 pi. The only thing you have to keep in mind that this delta theta should be calculated when you move along a closed path, say C, requiring that everywhere, at each point of this point, the field theta remains continuous and well-defined. The small gradients are obeyed. The condition of small gradients is robust and cannot be violated. And then you find out that the allowed value of this q can be 0, as in this case, 1, as in this case, but you can also start rotating this magnetization vector, not clockwise, not counterclockwise, but clockwise. You could have done something like this. See? It's again a vortex. But the vortex which gives me a full turn of magnetization, but in the negative direction. So therefore I may have -1. I can now continue this process. +2, -2, the whole set of integers. So this is the status which is called Z infinity. So how to parameterize something, how to characterize a vortex by a number, but not a simple number, but invariant number. What does it mean by invariant number? The good question, the immediate question here, which comes to your mind, what if I had changed the shape of my contour? I have a vortex. Suppose there's just this one which we have considered. That means that I draw more or less continuous distribution of my order parameter field or order parameter of the average value, or its vanishes, of course. This is more or less what I have. It looks like as if I have a charge here in electrostatics. I'm just displaying the vectors describing the resulting electric field of a local point-like charge. Right? You know from electrostatics, very simple. So I went along a circular path, and we know that we got, in this case, Q equal to 1. What do you think if I change slightly, deform this path like this? Will anything change? Yes or no? No. So what is the condition that the results will not depend on the choice of the contour, in your opinion? What should I avoid? Just look at this carefully.
Crossing the contours.
Crossing what?
2 contours.
I'm talking about a single one. I have a vortex. Vortex is a distribution of the vector field n. And contour is something which has nothing to do with n field. It's a contour on the coordinates in the coordinate plane. I'm just following this contour and looking what happens to my local magnetization. It changes by 2 pi. That's fine, the angle. But the question is, if I slightly modify the contour, nothing changes. So what is the condition I should obey? What will go wrong if I deform my contour and go through the center? This is a bad point. I cannot cross the center. Because here, the field at the angle phi is not well defined, polar coordinates. Therefore, I have no information here. I break the continuity condition. This is very much like in complex analysis. It appeals to analyticity. If you have a pole or you have some other kind of singularity, you may have branch cuts. You can define, as long as you are staying in the field, in the region of analyticity of your function, you can do whatever you wish with your contour. Deform it in the way. The only condition, it should not cross the singular condition. The same condition is here. So, the result should be such that it should not depend on the choice of the contour. So what is that? What is that feature which remains invariant in such a way? Here in this case, it's the so-called topological invariant. The topological invariant is defined as follows. First of all, we ask ourselves, what is n of x? This is a unit vector field which varies on the circle. This is the circle S1 sub n, which means this is the space of degeneracy of my orbital. Right? X, generally speaking, belongs on the plane, the coordinate plane. Coordinate plane not to be messed up with the space of degeneracy of the autoparameter. So therefore, n of x, as any function in mathematics, provides a map from this manifold, from this space, which is two-dimensional, planar, two-dimensional Euclidean space, to a circle. When you have f of x, you say, this is a map, x goes to f. You have to know the space when at the manifold. When x is defined, you have to know just the same for f, and you provide this map. When you write down, draw a function, f is a function of x, for n of x, you find the value f. You map this onto that. This is the meaning of the function. Okay? But here, in the case of vortices, we're not interested in the whole plane, coordinate plane. We choose a closed contour, C, X belongs to a closed contour C. Some closed contour, which is isomorphic to another circle. But this circle now is the one which is drawn here, and it is drawn on the plane, on the coordinate plane. So therefore I have two circles. One circle is the path C along which I move, and the other circle is the circle where the other parameter field or the magnetization varies. And this function provides a map from this to this.
Excuse me, sir.
Yeah.
So in the real space,
Yeah.
because there is no unique center point, right? Like we can start from any point. For example.
No, well, you are dealing. Okay. This is a very well posed mathematical question. You start with a smooth function f of x. You consider a smooth configuration of this vector field. This smooth configuration is such that it cannot be smooth everywhere. It is smooth almost everywhere except for some point, better to say except for some region, which we call the core of the vortex. We eliminate this point from the plane. In mathematics, you cannot play this games that as we physicists do. The mathematicians would immediately, remove this point with all this environment and throw it out. So we have a plane, and I have a hole inside this plane. It's absolutely clear that now if I draw a contour, Either a contour are such that it can be reduced to a point, shrink, they can be shrunk to a point, or they cannot, because they go around this hole. In case they go around the hole, this is the case of our vortex. So there is a limitation. You have done something with your space. In other words, it's not simply a plane. It's a plane R2 with one point thrown out.
And so our distribution is such that there is...
It's not about distribution. It's about no topology and the difference in topology of the Euclidean space and Euclidean space with holes.
So there can be more than one holes, right?
There may be more than one holes. This is a multi-vortex configurations. They play important role. It's actually, all this physics will be about that. But I'm talking about how to classify individual vortices. Why it is important, how they come about at all. Because originally, in this configuration, such things are forbidden. Because this theory requires that the field theta of x is defined everywhere. Theta of x is not defined here at all. It's a violation of the rules. So I now want, by force, it's tour de force, I want to enforce the Gaussian action to give me a possibility to describe vortices. Yeah. So this is the map from S1 to S1, and all these maps are well classified in mathematics, namely in mathematics which deal with topology, more accurately in the mathematics which deals with the so-called homotopy. So I will not go much into details, but I will only tell you one thing, namely that such maps S1 to S1, generally speaking, I may have some manifold X which is mapped to S1, and then I'm asking, are these maps interesting or not? And this has to do with the so-called, the fundamental of the first homotopy group, which describes the map of X onto S1, by asking, may I have this map, can it be a non-trivial? For instance, imagine that X is the surface of a two-dimensional sphere. Just a simple exercise, simple excursion into the field of topology. This is X. This is the surface of your sphere, the surface of a ball, which is the two-dimensional sphere. And 1 means S1. I want to map something onto the I want, right, where is who? Okay, so I want to consider some function. I want to consider a contour, a closed contour on the surface of this sphere. If I consider the closed circle on the surface of the sphere, if there are no points which are eliminated, excluded, I can shrink this closed circle to a point. Then I will say this map is trivial. But if it's sufficiently to make a hole on the surface of the sphere, I will have two classes of the closed contours, those which can be shrunk to a point and those which cannot. And the second necessarily go around the point which I have thrown out. This is an example that we have here. So, again, I give you only the direction of for your future interest to go deeper into the details of this transition. I can only tell you that now what you can do is to introduce the following number. It is the gradient of theta times dl. That's a circulation of this vector field along L, along some L, dl. It's a length element, and all in all, what I have, it's the center of my vortex, and this is the the contour C, which goes around this excluded point. Yeah, it's clear that this is actually the contour interval, and if I start from any point and go make a full turn along this contour, what I will find out will be just delta theta divided by 2 pi, and that will give me how many times the n vector made a full rotation in positive or negative directions before it came to the original position. And this is why Q belongs to this group Z infinity. Now you can simplify your life. Well, analyticity will tell you that no one precludes you from choosing a circular contour. Let's see now the contour of the sub-radius R, large enough from the center when we have an excluded point. Here is the angle phi. And now I would like to introduce the local basis, local orthogonal basis. This is E of R, a unit vector, and this is E of phi. It's clear when you go from point to point, both undergo rotations, but these are basis vectors. And absolutely clear that if I live on this circle, then dl will be directed along this field. It's a tangent direction because I will go along this way. But the length of this arc will be r d phi. You agree with me?
Yes.
Good. For the same reason, the gradient of theta, I will easily imagine, so it's an axial symmetry, should also have the same direction. It should be like this, and this should be d theta divided by r and d phi. So therefore, this quantity Q is 1 over 2 pi integral from 0 to 2 pi. Instead of this, I write down r d phi. Instead of this, I write down 1 over r d theta d phi. Scalar product gives me the square, which is 1. Everything cancels out, and I'm done with the result. And this is actually d phi, d theta d phi, and this is what I expect. This is the derivation of our original formula, initial formula, which is derived here using axial symmetry of the problem. The specific choice of the contour. You can check that if you deform this contour, the result will remain the same. That's the very well-known theorem in mathematics called the possible deformation of the contours in case these are closed. So this is an invariant. Given a vortex, Q is fixed and stable against small variations. That means that I can now a little bit go from a contour to a contour. I can also move my magnetization a little bit. Right? The Q will stay the same. A good question here would be if I have any kind of distribution such that how many configurations satisfy a given value of Q. One of them is just obvious, it's radial, right? This radial configuration, the radial vortex. But I can a little bit, deform this thing. Will my energy increase, or will we stay the same? Yes, the energy will increase because this turns out to provide you a local minimum of the energy. A symmetric vortex has a local minimum in energy. Every time you make it a little bit deformed, the energy increases. Which means that the ground state of the system with all the spins polarized is the solution of, is the result of minimization of your Gaussian action with the uniform and homogeneous boundary conditions that the gradient there is vanishes. And then you have ferromagnetism as the ground state. If you release this condition, if you allow yourself to have a distribution of the field which is not homogeneous on the remote boundary, then it turns out that there are new possibilities and new local minima. Those are associated with good vortices. Now the good question is, if we have a single vortex with Q, okay, so I have to say, nevertheless, I cannot make a systematic, convincing proof of that. All possible configurations, including those which contain singularities. It was your question, I don't remember. Is it possible to have more than one vortex? Yes, of course. Of course, we are talking about this. All possible configurations can be characterized by corresponding topological invariant Q. And all of them fall into the different classes. Each class is fixed by the value of Q. There is a class with Q equals 0. These are all configurations which are isomorphic to a ferromagnetic state. Well, what it means, but topologically equivalent. You know what topology is? For topology, this and this and this are the same objects. But because they can be obtained one from another by smooth, continuous deformations. For instance, if you have a torus, and you have a cup and mud. Is it what I'm saying? No, it is not. I can't even imagine. All right. So you better go and check for yourself. There are continuous deformations. You know, in other words, if I start with the ferromagnetic state, I can slightly deform it like I'm doing now, allowing vectors to deviate slightly from the, say, fixed direction of magnetization. But if I choose any contour, any closed contour, the delta phi is 0, delta theta is 0. So if I go somewhere, I go back to the initial case without making any circle, any full circle, any full rotation. So this is the class, this one. There is a class with +1. This is the all configurations with delta theta is when Q is +1. You could also modify and deform them a little bit, but whatever is the contour which encircles the singular point, you will get the same result for the topological invariant. And then you can prove that, do you know what the groups in mathematics are? Did you have a course on group theory? You have? You did? You haven't?
I did a little bit.
You did a little bit, okay. So these different classes form groups which operate according to the following law. So if I sum two vortices, I take two vortices, one with circulation, the invariant Q1 and the other Q2, and bring them together and enforce them to merge into one another, I will obtain a single vortex with vorticity or the invariant equal to Q1 plus Q2. In other words, if I have a vortex with Q equal +1 and anti-vortex with Q equal -1 and bring them together, the vortex disappears because I will get a configuration with Q equal to 0. So it's a group property. Right, so this is what this homotopy group P1S1 is just about this. Now you can ask, all right, what is the energy of a single vortex? From the construction that we already considered, it follows that this energy should diverge as the linear size of the system diverges. You understand why, right? And then we consider our radial field, radial distribution. Let this contour be just the boundary of your system, right? If somewhere inside there is a core of your vortex, then inside this domain you have a vortex-like distribution of this vector field. And if the domain is finite and has a boundary, then on the boundary you will have the same value of the topological invariant as you had for any other contour which encircles the singular point. But as we said, if the boundary is sufficiently remote from the center, from the origin, in other words, if the linear size of this R is large, then I go back into the expression of my energy or free energy or action V2x, and if I estimate this integral in the region close to the boundary, I have the gradient everywhere non-zero. Gradient square is a positive contribution to corresponding action, and therefore the larger is R, the more divergent will be the expression for S, and therefore the smaller will be the expression for the exponent of minus action. So such vortices, in other words, in the thermodynamic limit, are not expected to give a finite result. They don't have a finite probability to occur. Now, nevertheless, let us estimate this energy. This is the expression. It's J divided by 2 is radial theta square, and yes, and d2x. That's fine. So we again choose theta to be axially symmetric. So let theta in polar ordinates look as follows. Let it be, all right, let it be 1 over, right. Like this. Right. So then the gradient of theta is E phi 1 over R d theta d phi, and is Q divided by 2 P R. And so therefore the gradient squared is Q squared too many 2 pi's. This is it. I don't need this 2 pi at all. It's Q times phi, because if I make one full circle, theta will take from 0 to 2. Yes. So this is absolutely redundant. This is phi is simply Q squared divided by rho times this Q first power. If I now take this one, I have this one. All right. Yes, very good. And therefore, the whole expression will give me what? It gives me J divided by 2, integration over angles gives me 2 pi, and here I have from A naught up to the boundary of my system, I have Q squared here, and d rho divided by rho. That will give me J pi squared, y pi squared, Q squared, again, Q squared. Pi j, Q squared, and the logarithm of the radius divided by A. So this is the energy of a vortex, single vortex configuration with a topological charge Q. It's proportional to Q squared, which means that both for positive and negative charges, the result is the same. The result does depend on the magnitude of the topological charge. It's proportional to Q squared, but what is most important, it contains a large logarithm. Logarithm, which is linear size of the system. If you send the linear size to infinity, this is the version. Which means the vortex is always, from the energy point of view, is always an excitation. An excitation with the energy which diverges in the limit in the thermodynamic limit. So therefore, the singular vortex is not an appropriate object to deal with. But this conclusion is a little bit naive. Because what you need to do is to estimate not an energy of the vortex, but the free energy associated with the creation of the vortex. And if you do so, you will write down delta F for a single vortex is epsilon of Q minus T S of Q, when S of Q is the logarithm of the gamma of Q So what is the statistical weight of this vortex? In other words, how many possibilities can I encounter if I have a vortex on the plane? Well, we understand that if we go to a macroscopic picture of a discrete lattice, then the most natural thing is to associate the vortex with the center of elementary blockade, elementary square, such that for a radial vortex, the organization looks along the diagonal, right? So, if I have a lattice, I may have a vortex here, or here, or here, or here, and so on and so on. The degeneracy will be simply equal to the number of plaquettes. And the number of plaquettes is the same as the number of the sides. Or at least proportional. So therefore, it's a logarithm. Gamma should be the area of the system divided by the elementary area. This is the number of your plaquettes, and we'll do it twice. Logarithm R divided by E. Now I combine the results, and I can see that delta F of Q gives me what? Gives me pi j Q squared minus twice T and the log. A very nice expression, because it tells me that delta F may have any sign, depending on the temperature. If the quantity in the brackets is positive, in other words, if the temperature is less than some special temperature, PQ star, which is PJQ star divided by 2. I just said, I don't like this too. Maybe I made a mistake somewhere. Yeah, everything's right here. If the temperature is like it's written here, then the square root, the expression in the brackets is positive, and delta F is positive, which means that the vortex represents an excitation. This is observation number one. The second observation, that means that the free energy associated with the creation of the vortex is positive. The system itself does not maintain vortices. The system must be excited for the vortices to appear. But even that is not quite correct, because if I have a single vortex with a charge Q, for an infinite system, I cannot allow myself such a luxury. I cannot have even a single vortex. Why? Because in the limit when R goes to infinity, delta F becomes infinite large. Correspondingly, the action of a single vortex becomes infinite large, and these vortices are out of. Now, suppose that I have now a system of vortices. I have vortex Q minus Q. Okay, let me write it down like 1, somewhere minus 1, 2, minus 3, minus 1 again, plus 1, minus 4, and so forth. So I just distributed the centers of the vortices on the plane and attributed the corresponding topological charges to each of those vortices, right? Such that I can introduce now Q large, which is sum of all I from 1 to n vortices, let me call them and start, Q large. The total charge, total topological charge. If I calculate the energy of such system, of many vortex system, the only thing that will change here will be this. Just recall electrostatics. If you have electric charges distributed, let this Q be the charges of your system. And let the Q be the total charge of your system. What is the electric field created by the system of charges at distances much greater than the region when your charges are located? In other words, it's not like all the plane is more or less uniformly distributed, populated by the charges, but some part of that. The charges are located in some domain, within some domain, somewhere here, and you're looking at the effective field far away from this region. Then what matters is not how these partial charges are distributed inside. What matters is the total charge. The whole system will appear as a single charge, single point-like charge, because the distance is very large. So therefore, this approximation will be more or less justified. If Q has the total charge, I will have the electric field of a single charge Q. And this is the energy which I will have. By the way, this logarithm, have you ever tried to solve the electrostatics? Not in 3, but in 2 dimensions? What is the potential of electrostatic potential of a Coulomb, of the Coulomb point-like charge in 2 dimensions? Questions? You are already graduate students, right? You are supposed to know this answer. The potential in 3 dimensions is 1 over r. Okay? You are solving just the Laplace equation, nothing like that. Suppose your dimension is 2, not 3. It's the same law. We are doing electrostatics in 2 dimensions, in fact. It's nothing but what I'm saying now all the way. The only novelty is that on top of electrostatics deals only with point-like charges and the fields created by those charges and the potentials which describe those fields. Right? Now, this phase transition theory, which we're dealing with now, gives you a size slightly more than that. It gives you, there are some distribution of the fields which can be interpreted as if I have a a vector field associated very similar to an electric field in electrostatics. I realize that through my auxiliary field theta, which has a completely different physical meaning in the context of two-dimensional x-y. So from this you conclude that if you want such configuration to contribute to physics, please be so kind and impose a very, very strong restriction. Your system must be electroneutral. You have to have as many positive charges as negative ones. You may also make another observation, that since the energy of an individual charge, topological charge, is q squared, the larger q, the higher the energy. So the minimal non-zero contribution comes from the minimal value of q. So therefore it is quite reasonable to restrict your configuration only by vortices and anti-vortices with the minimal values of these topological charges, plus or minus 1. You don't go for 2, 3, 25, and so forth. Because these are characterized by extremely high excitation energies. Okay? So let us now understand the meaning of this formula. So as long as T is less than T star, delta F is positive, and your vortices are excitations. But if the temperature is above, but if you are above that temperature, delta F becomes negative. And therefore isolated charges are spontaneously created and proliferate across the whole system. In view of this restriction, I can only say that basically what you have at any temperature. So first and foremost, in this restriction, let us set modulus Q equal to 1, and therefore this T star temperature is simply given by Qj divided by 2. And this is in a very rough approximation into is the temperature of the BKT transition, Berezovsky-Kosterlitz-Stahl, is the temperature of this topological phase transition. So you have positive charges, you have negative charges, positive, negative. You have a plasma of vortices and anti-vortices. But this plasma has a very peculiar property. The logarithm is a potential. But as any potential in Coulomb, in any Coulomb problem, whatever is the space dimensionality, charges of the same sign repel each other. Charges with opposite signs attract each other. Right? Okay. Now when the temperature, so if I have charges, positive charges among themselves as well as negative will tend to repel each other. But positive and negative will have a tendency to come closer to each other and form dipoles. So therefore, at low temperatures, what you expect to happen is a creation of neutral dipole pairs. Some of them may be of larger size, some of them may be of smaller size. But the thing is that the linear size, the size of this bound state of positive and negative charges, the size of dipoles, turns out that low temperature is much, much smaller than the distance between these bound states. Right? So I have a dipole in here, dipole here, and dipole there, and the typical distances between them. It's much, much greater than the linear size of each dipole. Now imagine you are asking yourself, this also must be within the course of field theory at your university when you are still undergraduate students. If you look at the electric field of a dipole and compare with the electric field with an isolated charge, which is stronger? What? Dipole will be stronger. Oh, it should be just the opposite, because they tend to cancel each other, right? If you take a dipole with a plus and minus size charge, right, located somewhere in space, and go to distances far away sufficiently as compared to the linear size, what do you see? You see a neutral object, right? To understand that the dipole has a structure, you have to get inside. You have to be at the distances comparable to the distance between them. If you are far away, you see a neutral object. All right? So therefore, if the condition that the distance between the dipole pairs is large, and that means that the concentration of these dipole pairs is small. The smaller the concentration, the larger the distance between dipoles, right? Then you basically have the picture that you can derive from the Gaussian model, which ignores completely vortices. So therefore, vortices are excitations. They only exist as vortex-antivortex dipole pairs, and they do not affect significantly the physics. They only normalize some quantities. You again have power law correlations with some modified values of the parameters, but basically the physics remain the same. In the spirit of what we have already learned about perturbations, you can say that vortices and anti-vortices in that temperature range represent irrelevant perturbations. They don't affect the critical behavior. Don't forget the critical behavior in the XY model, in the planar model, it's not a point as the whole temperature region. The whole temperature, lower temperature region is not significantly affected by the vortices. This is why the Gaussian model is good. But if you increase the temperature and reach this value of the temperature, what happens physically is the following. Since there is a statistical distribution of the pairs of smaller radius, smaller size, increase in number, and start to decrease the effective attractive forces between the plus and minus charges of larger pairs. So they screen that effective field. Screening means that the bound states is no longer that stable and so robust as it used to be before. Like in an isolator, right? So if you take an isolator and in the vacuum you have the law E squared divided by R, in the isolator you write down this epsilon, which is greater than 1, and decrease the potential. This is exactly what happens. And at some point, the screening turns out to be so large that your dipoles dissociate. No bound states exist in this case. And this is the case when singular vortices start proliferating along the whole system. In other words, at low temperatures, you have a phase, a dipole phase. At high temperatures, you have a typical plasma phase when the density of positive and negative charges are comparable, and when the correlations are comparable, and when no pairs are formed. You have a plasma, or more or less uniformly distributed plus and minus charges. And it should be in any plasma. There should be the so-called Debye screening length, a finite screening length in this plasma regime. And this device screening length is nothing but the correlation length of your system. This is the way the correlation length emerges. And this precisely is the nature of phase transition. The phase transition is nothing but the transition associated with the dissociation of the dipole pairs of vortices and anti-vortices. So the outcome of all this story is highly non-trivial. This is a very special example of a system with unbroken symmetry. You never break the symmetry. You always stay in the disordered phase. But you can be disordered as you are disordered at criticality, when you are not have reached the regime when the average non-zero magnetization appears. But their correlations behave, decay exponentially. Or you may be deep into disordered phase when the final correlation. It turns out that there is a phase transition between the regions, and the origin of this transition has to do with topology. And I understand you, this is the simplest possible imaginable example of application of topology in condensed matter physics, because all the others are associated with much more complicated things. Other groups, the so-called nonlinear sigma models, and other manifolds, higher order spheres, and things like that. But this is the simplest part. Well, that's the end of the story. Of course, I didn't tell you a lot. I told you only qualitatively what this phase transition is about. At least if we summarize what we have learned during the course, I think, in much detail discussed the case of an Ising model, which is an example, a typical example of a system with discrete symmetry. We described such powerful, historically justified method as mean field, or later on which transformed into a Landau theory of phase transition. We also consider possible inhomogeneous in the distribution of the order parameter field and introduce the Gisborg-Landau expansion. And a similar expansion, I'm sure you already are discussing in the lectures of Professor Kiselev, in conjunction with the theory of superconductors and superfluids. We have found amazing things happening beyond mean field. First of all, we found out what the upper critical dimension is. We know also that there is also a lower critical dimension, which has to do with some restrictions upon ordering, both in systems with discrete symmetry and continuous symmetry. In the latter case, we discussed in some detail the famous Mermin-Wagner theorem, whereas for discrete systems we discussed the Landau-Parens theorem, which is quite a lot, as you can see. And we also considered, we made a first step in the field of renormalization and scaling. We already know what the fixed point action is, what the scale invariance means, and how perturbations to these scale invariant situations are classified. And finally, we considered a few exactly solvable models, one of them being one-dimensional Ising model, where we checked the validity of the RG ideas. We have demonstrated that it is fruitful, it is informative, apart from the exact solution using the transfer matrix. Right? And finally, we considered the continuous model of planar spins in 2 dimensions, and found out an amazing property that with unbroken symmetry of this model, there's still room for a phase transition of a completely different origin. The mechanism turned out to be nothing to do with what we have learned so far. It has to do with some topology and topological objects which emerge with the peculiarities of the group symmetry of the model. So I personally consider this as an introduction. This course should have been called not the phase transition, but introduction to the theory of phase transition. Because the real things start later. If you get interested in all this, or you will start working in the field on questions and problems somehow related, you will be forced to go deeper in all this, and you will enjoy this wonderful, beautiful field of the theory of phase transition because, in my opinion, because it's, well, it is deep, profound, full of ideas, and it can be realized using very nice, tailored field theory, of which I just always been fond of and spent most of my life in this field. So it was a pleasure to deal with you, to be with you during all these 12 lectures. Please take seriously all those remaining problems. You are supposed to submit them on Monday. Why you should be serious? Because this will be the second homework. To me, knowing what you have done and what you haven't done would be much more instructive than accepting the exam, taking the exam, organizing the exam for you without the second assignment. The second assignment you can and you should treat as an introduction to the exam. It will be a significant part of your exam. I will be taken seriously, very seriously. All right? So we meet on Monday at the same time, same place, but as far as I remember, the exam is planned for March the 5th, if I'm not mistaken, in the room H, not this one. Everything is oversubscribed. Okay, see you on Monday.
Even beyond, because we'll have the tutorials, even if you have concerns beyond